Piotr asked me yesterday if I stopped using handwritten notes, and I said, no, I just use iPads, there is no need. But this morning I was panicking, trying to revive it, because there was no battery to charge last night. So there is still advantage to handwritten notes. In any case, I will write less than I plan to do because of the board space. And this is a 2-3 year project of Yatir, Asaf, and myself. So this is joint work with Yatir and Asaf Hassan. That started during COVID, I think, right? Yeah, we were for a long time conversing only on Zoom. And the goal was, or is, to analyze, I guess, algebraic objects, groups and fields in certain, I'll talk about collection of tame valued fields, but to analyze interpretable ones, so it means quotients of by definable equivalence relation, but somehow to avoid elimination of imaginaries. So this is kind of a lazy person approach maybe to interpretable objects, partly because in some of the settings we'll be talking about elimination of imaginaries. There are no theorems yet about elimination of imaginaries. But also, even when there are, as we saw yesterday in Deidre's talk, just understanding algebraic objects in terms of the geometric sorts is not simple always, can be quite complicated. So as I will describe, we are trying a different approach. And just so it is clear that you're not listening, because probably each one of you heard one of us speak about that in the last few years. So to clarify that you're not listening to the same talk all over again every time, let me just point out what we did. So there was one paper we posted where we analyzed interpretable fields, and we showed that they are, as you expect, definably isomorphic to finite extensions of either the value field or the residue field. And then there was another paper in which we started working on groups in general, and we gave some results on DP minimal groups and about groups having unbounded exponent in this setting that I will describe. And a few months ago, we already posted an article on this subject only in the p-adics, or in p-adically closed fields, but then we realized after a while that the project was stuck, that we can do it again in all the 3 settings that I will talk about. So this is a relatively recent result, which extends, whoever saw the paper on the p-adics, extends the result on the p-adics. All right, so soon I'll put on the side the settings that we are talking about, but let me just clarify, first of all, what this is for us, because all the rest, I think, at least is clear. Maybe the various is not so clear, but we'll explain that. So what do I mean by a group being definably semisimple? So for us, this will mean that there is no infinite definable normal abelian subgroup. So this is the definition I will take in this talk. So in particular, it's definably simple. If it's non-abelian, it's non-abelian and definably simple. And an issue come up, you may think immediately whether this infinite, is this preserved under elementary equivalence, or it depends, of course, when you can eliminate in MEQ, there exists infinity or not. Hopefully, I'll say a word about that at the very end. So what are the settings that we'll be looking at? Now I'm explaining the various valued fields. So these are 3, basically. One is real closed valued fields, but actually more generally, what is called T convex, polynomially bounded, or more generally power bounded structures. And let me explain what these are. So you start with an O minimal. So T stands for the theory of O minimal structure. So you start with M satisfying T expansion of algebraically closed field. O minimal P bounded, whatever P means, polynomially bounded or power bounded. And then you, in it, you fix a ring which is more than just a valuation ring. It's a ring which is closed under all continuous O minimal zero definable functions. So you get a valued field which expands the O minimal structure, and Lau van den Ries and Adam Lowenberg analyze that into one paper, joint paper, and one paper with Lau, and I will describe what properties we are using from that. Okay, and this is the situation where we don't have EI, as far as I know. 2 is ACVF00, and some, or I think maybe all, what's called V minimal expansions that I will not define. And 3 is periodically closed fields. So these are fields which are elementary equivalent to finite extensions of the periodic field. So this is what I mean in this talk by various valued fields. And I can put the main theorem, or the theorem that I want to discuss. So assume G, well, you might as well assume infinite because we will not care so much about finiteness, is interpretable in 1 to 3, and, or if G is definably semisimple, as I described on the left, then we have the following. First, there is a finite normal subgroup N of G. And what we're saying is really about G mod N. In G mod N, there is a finite index subgroup, a group of finite index. There is G0 of finite index in G. Yeah, everything definable. Definable, yeah. All the objects I will talk about will be definable, and I will not use the language that Will Johnson is using, saying interpretable when I talk about definable subset of interpretable object. I will just use definable all the time, even though it is definable in the sense that it's interpretable, right? G is interpretable, and I will be very precise when I will say that it is definable in the old sense of the valued field. What do you mean? I work in a saturated setting at this point. No, yeah, I work in any of these settings, whatever the setting is. Yeah, not in the group language, not in the group language. Maybe it is, but I don't know. No, I don't think it is. Such that G0, well, I can write it like that, is definably isomorphic to a product. Can you see when I write so low? Not so much, huh? okay? Such that H1 is a linear group. Okay, now I'll put some notation. So this is the notation. I'm using Diderot's notation, valued field sort. And H2, the same thing, is in the residue field sort. Now in the p-adic case, of course, this is finite, so you don't need this part, because the residue field is finite. So you can say that G is isogenous to this product, in the sense that you mod out by a finite index subgroup, you take a finite index, sorry, by a finite subgroup, take a finite index subgroup, and then you get a product like that. So, few remarks. So, first of all, it reduces the problem to definable subgroups, either of the residue field or of the valued field sort. In the residue field, we're in good shape. In the T-convex case, this is an O-minimal structure. This is actually a model of T. This is the result of Van den Vries. And then in O-minimal structures, we know that these linear groups are in fact semi-algebraic groups in the sense of the real closed field K. And in the ACVF case, this is an algebraic group inside an algebraic group because the residue field is just ACF. In the valued field case, this is really part of a project for which there exists a preprint. So analyzing definably semi-simple groups in various valued fields, but many more various than ours, and Cillian fields, I think, in general. So there is a preprint, not preprint yet, but they were nice enough to show us of Halipchuk and Gismatulin and McPherson. So this is work in progress, and all we do, I should say, is reduce to this problem, although one can read off from the results. I think more or less it's true that H1 is like an open subgroup of maybe of a simple algebraic group. I don't know if it's true. Dougal will. I think it's more or less true, no? That this will be an open subgroup of a simple, not simple, semi-simple algebraic group. I should say one small glitch, but I think it will be resolved once this preprint is clearer, that we don't know yet that H1, we know that H2 must be semi-simple. We don't know yet that H1 must also, so we don't know that the semi-simplicity of G goes down to H1, but we're almost sure it is, because the Lie algebra will have to be, so using arguments of Lie algebra, probably H1 is definably semi-simple, but this depends on. The n is central. You can always, yeah, the n is central.
Yeah, but in the case of differentially closed fields,
yes?
there's an argument to say that it's the same.
Okay.
That if you have a definable subgroup in the quotient by an abelian central, but it's in the differential case of.
No, I think so. I don't know if we get n to be central in G, but we get n to be central in a finite index subgroup of G,
sure.
and
That's
then
enough.
We get that.
Enough.
Yes, we do get that. No, if H1. No, but we don't know the G0 either. We don't know. It's not clear that G0 is. It's not clear why it immediately is. Because maybe you have a small abelian normal subgroup that you take one conjugate of it, and we don't know. Maybe. Okay, so what I want to do in the rest of the time is to basically describe the strategy of the proof.
Could you swap the board so I can read the entire theorem when you prove it?
Sorry? Yeah, this is important, eh?
I would like to read the.
Yeah. Really? You're sure you want the whole theorem?
My suggestion was to swap the two.
All right.
So the theorem's at the top and the other things.
You're right. You're absolutely right. Also, I can move it first to the first rows people, and then move it up to the other ones. We can go back and forth as well. No, no. Can you see now? Is this okay? Okay, I will not do board washing. Board washing is reserved for the experts. Yes. Everything is definable. So the isomorphism is definable. So H1 and H2 are definable as well. Yeah, everything, definably isomorphic. So. Okay, so let me describe the strategy, because and this will also describe the last 3 years project. So I will call it the bottom-up approach. Somehow I think of EI as the top-down approach, where you analyze the whole, object in terms of geometric sorts, and then you go down to the sort, and we are doing something the opposite way. Okay, so the first thing that we do, and G is just any interpretable group. Now you don't need even, this goes back to our previous work. And I'm going to ignore all this n, so I will always say after modding out by a finite subgroup, after modding out a finite normal, of course, subgroup, we can find a definable infinite set S in G, such that S can be injected, always definably, into one of 4 sorts. So the 4 sorts that will play the role, will be the major role, play a major role in this talk, will be the value field, as we said, the residue field, the value group, and the last sort is the zero ball. So this is K mod O and O. So these are the closed zero balls. Of course, not to all of them, to either this one, or this one, or this one, and sometimes to all of them. So what we are saying is that every definable, if you allow finite to one map, then just whenever, this is not even a complicated result, every interpretable object has in it a little piece, either of the big field, or the residue field, or gamma, or K mod O. Now this could be very, very small relative to the whole G. But now we start with it, and somehow like Zilber intercomposability, you can say we start generating bigger and bigger group inside G. So this is what I mean the bottom up. You have inside big G maybe a little piece which goes into little k, and then you have a small neighbor, a small set, you start generating more or less what you get from it, and you get like some sort of avatar of k living inside G. And the idea is to analyze G via this set. Now let me put a notation that Yatir will like, he's never seen it. Let's say that, let's write G goes into D, where D is one of these 4, if there is S infinite, always definable, in G, such that S injects into D to the M. Nice.
Got any parentheses?
Okay, so the theorem said that you can always, G is always locally injected like this into one of the 4 sorts. And let's say that if G does not inject like this locally into G, then we call G is what we call D-free. It has no trace of this sort D. So this is for D being one of K, little k, gamma, or K mod O.
This means that S somehow sits in like many copies of little k, or how does it?
Why? No, it sits inside little k. It's injected into little k.
Yeah, but like if dk is like something periodical, small k is fine.
Right. No, then it doesn't, we are not interested in it. It cannot be injected into the residue field if it's infinite. So in the periodic case, of course, there is no little k. Because has to be injected here, so it cannot. Yeah, thanks. This is important, of course. In the periodic, you don't need that. Sorry, I cannot. Well, here in this step, we actually get it to be in D itself, but because of properties of each one of them. But at the end, we don't care. Because we're going to move up in rank, then it will have to go into power of that. Okay, and then still part of, you can say 1.1, and this goes to our second paper. So again, after modding out by finite subgroup, after modding out finite subgroup, normal subgroup,
11 or 1.1?
1.1. If you cannot see it here, I'm sure. They are sure that it's 11 over there. So again, D, my D will be always one of the four distinguished, Ds for distinguished sorts. And the statement is that if G locally injects into D like that, so it has a piece, an avatar of D in it, then there is a global, so this is a big type definable group, that I will call a subgroup, yes?
What does global mean?
No, it's not a small collection of formulas. It's a big collection of formulas. Like the infinitesimal, I will say in a second, so hopefully. In G, so it's a type definable subgroup in elementary extensions as well. It remains type definable subgroup. With, okay, let me introduce this, the rank of this, and I will say in a second what I mean by rank, being the maximal rank of some S which is injected into DM. Okay, so now what do? You have, so first of all, let me say that the rank that I'll be using, well, is DP rank, but in each one of them, it corresponds to the natural dimension on the sort. So each one of them has a natural dimension, maybe not K mod O, I'll say something about K mod O, but you can, so once you talk about, oh, sorry, I will say that, and nu D is definably injected into D, not to the M, but D to the K for some K.
But I mean, new D is a subgroup of, okay.
So let's see what I mean by that. So you have a type definable group, and the way to think of it, think of the group as being the infinitesimal group inside little k, if k is O minimal, or the infinitesimal group in, say, capital K, if K has order or not order, just with evaluation. So this is a small group, type definable group, and it lives as a type definable object, it lives actually inside d to the k. Okay, so on one hand, it's a type definable subgroup of G, but as an object, as a type definable group by itself, it lives inside d to the k. So it lives inside one of these sorts. Now, we say even more than that. When d is either gamma or k mod O, then we can say more. Actually, the way it's injected is not only as some type definable group, then nu d is injected into the group structure, or k mod O to the n plus. So a subgroup. So actually you have a copy of, let's say, the infinitesimals inside the order vector space living as a subgroup of your G. Or you have a copy, well, here, and in this case, actually, I'll say it, we get even a definable group. Nu D can be chosen to be definable in K mod O to the n. I hope, does it make sense? So already this is quite informative. For example, we get from that the group in all these settings must have unbounded exponent, because these groups have unbounded exponent. It K mod O in the p-adic. This is like the first, how do you say that? Pfister group. So it's not torsion-free, but in all of these cases, by different reasons, nu D has to be unbounded exponent, so G itself must have unbounded exponent because of that.
And all these are abelian, right?
Sorry? And abelian. No, these two are abelian, but here it's not abelian by any means. In the K case and the little k case, we are not claiming that it's a subgroup. Yeah, these are abelian. You're right. You're right. Yeah, you're right. And the project, this is what I mean, the bottom-up project. The goal is to somehow analyze G via these four groups. The groups nu little k, nu capital K, nu gamma, and nu k mod O, when they exist, of course. So the picture is,
I mean, are you claiming that any definable group has the new little k, new big K, new gamma?
no, only if it injects locally into it. Sorry?
Nu K could be trivial. One of them.
Okay, sorry.
Yeah, each one of them could be trivial, but not all of them can be trivial. Maybe I should say here a little bit more, is that each one of these group, okay, maybe I'll say it later, is invariant under, it's not normal, but invariant under conjugation from the model you work with. So all of these four types are invariant under, as a type, they are invariant under conjugations by elements of the model in which you work, not in elementary extensions, by the models, and this will play some role later. This will be important. So we have like four little groups. I guess this is four. Sitting inside G, they don't have any interaction between them. Actually, we can show that the interaction, the intersection is trivial. It's just the identity element. And somehow, but this can be very, very little. with respect to the whole of G. We don't know, I mean, one of the problems we don't know, is the sum of the DP ranks equal to the DP rank of G? We don't know. In our case, it will be, because at the end, you can think of this. Here new K, capital K will live, and here new little k will live, and this captures everything. So you will get the full DP rank coming out of these two, capital K rank and little k rank. So this will happen here, but in general, we don't know, for example, if the sum of the 4 DP ranks equals the DP rank of G.
I have a question.
Yes?
Do you exclude, I mean, do you assume that your G does not project onto an abelian variety?
No, we don't.
So you could have that.
I didn't think of that, but
Because
can you have one of these projecting onto an abelian variety? I don't.
No,
I
I'm
don't.
not saying this, but G, the definition of semisimple.
No, it does not. No, it's just no infinite normal definable abelian subgroup. That's it.
It's not even made out of field elements, or is it just
No, what I'm saying, yeah.
Okay, so this was all preliminary. Let's see how much I can do. And now assume G, this is true for any G. Assume G is definably semisimple. And let's fix one of these settings. I don't want to work in all 3 of them. And my favorite setting is the T-convex, as you can imagine. So let's say we work in the T-convex. You need to, the proofs are similar, but they're not identical. This is part of the problem in producing a paper where you don't want to repeat the proofs, but then you cannot, yeah, this is a challenge, how to write it all together, because there are similarities, but there are differences. So now let's say that M is T-convex, P-bounded structure. And as I said, let me just put here that Van den Dries and Lowenberg, in 2 papers, one joint, one separate, show that K is, the residue field is a model of T itself, so it's O minimal. And gamma is just an ordered vector space. And this is why you need polynomial boundedness. Otherwise, it is not. And we have these 4 type definable groups in there. And the main obstacle is to eliminate nu gamma and nu k mod O. So we want to show that these 2 cannot exist inside. And then we are left only with little k and capital K. And as you will see, it's very fast from there. So the goal, eliminate nu gamma and nu k mod O and show that they cannot exist under definable semi-simplicity. Okay. Sorry? Now it will be, because I'm working in this setting, not the p-adic setting, so it will be an ordered vector space, so it will be divisible. Well, it's not over Q actually, because you allow powers, so you get a little bit, you have what's called the field of scalars. You allow x to the alphas as well. In the model of T, this is what I call power bounded. So you do get a little bit more than just the rationals. You have a field of exponents, what they call.
but not the full residue field?
No, it's not definable. This is a bounded collection of scalar multiplications. Okay, so let's start with gamma. And for gamma, we have, again, a general result, which does not involve the assumption of definable semi-simplicity, but as you will see, G any, if G locally injects into gamma, so I remind you, it means that there is a definable infinite set which injects into gamma, then there is, let's call it G0 again, G0 normal in G, finite index, such that nu gamma implies, in the strong sense, that one of the definable sets in nu gamma actually lives in the center of G1, of G0. So you have a definable set in this type, and if you want in this infinitesimal type, you have a definable set which lives in the center. In particular, it's infinite. So the center of G0 is infinite, and then because G0 was normal in G, and the center is infinite, you get an infinite abelian normal subgroup definable in G, right? So G has infinite normal abelian subgroup. So if it's definably semisimple, you cannot locally inject into gamma. So we removed gamma. I can say, I don't want to go deep, I can say a word about that. The reason is, okay, I don't know if I can fit a proof into here, I doubt, but let's say that nu gamma, as I said, is actually a subgroup of an order vector space. Okay, think of it as the infinitesimals in the order vector space. And now conjugation by G, it doesn't keep nu gamma as a set working in a big structure. It does not preserve. It's not normal, but locally it is. So locally, when you have the map x goes to x to the G, acts locally on gamma on nu gamma, so on nu gamma to the n. But in order vector spaces, you cannot have even local families of local isomorphisms of an ordered vector space are not definable in an ordered vector space. So you cannot have infinitely many different actions by conjugations on a germ of gamma at 0. So it means that the way G acts locally on gamma to the n is only via finitely many automorphism, and then it's not hard to continue from there. Okay, so we're exploiting the fact that ordered vector spaces do not have definable family, even of local automorphism.
Could you have that the new gammas and the conjugates are sort of in direct sum?
No, because as I said, that you always have neighborhoods which are invariant under gamma, under conjugation. So locally, they intersect.
But at the level of G, they will be invariant from the conjugation?
On the level of G, sorry?
No, but that you find them normal in G0, but it will be also in G.
I didn't understand. So G acts on nu gamma. So you have a map from G going into the family of local automorphisms of gamma to the n.
But why is that?
Well, because every G acts. You just have this map is an action on the family of germs on germs of gamma to the n. So it acts locally.
I think she's saying, suppose you already accept that G0, the finite index subgroup, acts trivially on it.
Yes.
What about G mod G0? Maybe there's a two-element
That's
group.
exactly what I'm saying. Maybe it's swapping two copies of your group.
Then you have to show that the sum of these two copies somehow stays abelian in the group.
Well, that's true.
No, I'm missing something. So you have an open set inside gamma to the n, which is invariant. For every G, you have an open set inside gamma to the n, which is invariant under conjugation. So this is part of the fact that you get when we produce the groups. So the whole neighborhood, so you have a local automorphism of the whole open set, of the open set.
Yeah, but suppose it's trivial under G0.
But G0 is still fast.
But you see,
get
my
G0
problem is that
because,
if you have two copies of a simple group, it could be that your new gamma lives in one of them and gets swapped to the other one. Okay? You see, if G is an extension of order 2 of 2, no? Why not?
I'm not sure I understand, but the way I think of it, G embeds into the automorphism, the groups of definable automorphism of a germ at 0. And the image has to be finite. Maps into.
So she's asking what if the image has 2 elements?
Yeah, then the kernel has finite index, and the kernel acts. So you're asking what happens if a set acts trivially in the neighborhood? Why does it have trivially? Okay, so it's a good point. And because of definable connectedness, because you have notion of definable connectedness in gamma to the n, you can actually find when you fix any definably connected open set in gamma to the n, it will stay fixed on it. So not every G will contribute a smaller. Yeah, I don't know if this is the issue.
No, because it's not a neighborhood in G, not in gamma, but maybe we should continue on this.
Okay. Let's.
Yeah, the project is definable as well, but it's not clear that it's stability.
I don't think this is the path we're taking, but we can talk about it.
Okay.
I mean, this is how we show it's a group.
Okay, so what we have so far, if G is definably semisimple, then G is gamma free. So we already threw out gamma. Next, somehow the order here is a bit important. Assume G locally injects into little k, the O minimal field. Then, as we said, nu k is not a subgroup anymore, but it injects into k to the n, not as a subgroup, just injective set. So you can identify nu k actually with an infinitesimal subgroup inside, infinitesimal not subgroup, infinitesimal group inside k to the n, because k is an O minimal field. When you have a group, type definable or definable, then nu k admits the structure of a k differentiable Lie group.
So that was my question before.
Okay.
Why does it imply that it's an abelian variety?
What? No, what did I say?
That it does not have why does it imply that it's a linear group?
What is? I didn't yet have it. There is no linear group yet. No, nothing yet.
Well, Lie group is a linear group.
No, Lie group is not a linear group. It just means that it has a differentiable structure near the identity. Once it has a differentiable structure near the identity, and we know that every element of G locally in some small set around E preserves this open set, then we have the adjoint representation. For every G in G, with respect to little k, we send G to the differential of the map x goes to x to the G with respect to the little field k.
So dk is locally normal?
Sorry? Yeah, it's locally normal, exactly.
All 4 groups?
All 4 groups are locally normal. And this differential you can think as living, and now we have the linear group. You just take the matrix of the differential at the identity of this map. Locally, it looks like an O minimal map in a neighborhood, in a small neighborhood of E, of the identity inside nu k. So you use nu k as if it was a Lie group, because all you need is the local behavior of conjugation map. So you have a function going from G already D to GLN k. The same thing you do, by the way, with capital K. Exactly the same trick.
And you know that this is Yeah, and you know that this is an injection.
No, it's not an injection. This is because this I just think of it as sitting.
Sure.
Yeah, but this is not an injection. So now we do the following. We let H1 be the kernel of this adjoint K, let's call it adjoint K map. This is the part we have to keep analyzing. And we look at H2 being the centralizer in G of H1. And I'll write, then we get, and we show then one, that H1 times H2 has finite index. So these are both normal. This is normal, just being the kernel. This is normal, being the centralizer. Finite index in G. 2. H1 now is also K-free. We already removed we can show that all the little k part lives in H2. 3. The map from H2 restricted to H2 is finite to 1, from H2 into GL and K is finite to 1. And 4 is cheating. This is not true, but I will write it anyway, that H1 is definably semisimple. So it's not true. We don't know, we know something weaker than that, but let's assume some cheating. H1 is definably semisimple. We have some trace of that, but not exactly that. Sorry? Yes, and H1. Yeah, I think it follows from this, right? The intersection is finite. So in terms of the, we have the full theorem here. Yeah. So we already have in our hand H2. Really, this is the H2 that we have there. And now we are in the following situation. Now I replace H1 by G, let's call it G again. So now, replace G by H1 or H1 by G, I don't know. So now we have G is both K-free and gamma-free. We removed already these parts. And the main problem, and this is where we were stuck for a long time, and this is why we had one solution of that in the p-adics, but we couldn't find a solution in the other settings. And so, main problem now, eliminate K mod O, because I think once we eliminate K mod O, you can guess how it will go. We will do exactly the same thing. We'll have the adjoint representation with respect to capital K, because at least in our case, locally, everything is O minimal in capital K in the valued field. You have a good theory of differentials, everything, exactly the same argument, more or less replace little k with capital K, and you'll get an adjoint representation into GLN capital K. But the problem was that. I think this is my favorite part, but I don't think I'll get to say much about this. So let me just write. So now, assume then the G locally injects into K mod O. K mod O in general is the mysterious object. We know a little bit about the structure of definable sets that are somehow locally affine. On the other hand, it is not stably embedded. So it's a bit mysterious, and I encourage people, I think, yeah, people expressed interest in studying it. So actually, our result about new K mod O was stronger. I didn't say that. So in fact, what we had before, we know that new K mod O is actually can be chosen to be definable. Can be chosen definable instead of type definable, in this case. Let's call it H. So we have H, abelian, as Zoe pointed out, inside G definable. H is really isomorphic to a subgroup of K mod O to the n plus, so the additive group, as a group now. It's a stronger situation than we have in the little k and capital K. So of course it's infinite, abelian, it's almost contradiction to semi-simplicity, but it's not normal a priori. So the theorem that we prove yeah, I guess this is the best I can say, that for every G in G, if H to the G is different than H, then I think this is true. H, G times H, now, which is not H, of course, can be injected into, actually, it's even, no, I think, sorry? Yeah, sorry, but I'm now thinking, I think it's indefinable by ejection. It's not a group, notice, G times H is not a group. By ejection,
So it's not the group generated by, it's just the product.
right, it's just the product of two groups. To subsets, let's call it S1 cross S2, where S1 is in K mod O to the n, S2 is in little k to the m, and the dp rank of HGH is greater than the dp rank of H. Now, if G is K-free, then this cannot exist. And then we got a set of higher dp rank which injects into K mod O to the n, right? So if G is little k-free, then we get HG inject into some K mod O to the n, but it has higher dp rank, contradicting the maximality of H, the way we chose
When you
H.
say inject, what do you mean by inject?
As a set.
Does it, yeah, so it doesn't preserve any kind of group law or anything.
Right, but it doesn't. We don't care. In fact, because in K mod O everything is locally affine, it does preserve, but we don't care.
Yeah,
Because all we want from our sets just to be injected into the sort.
that's right, and no preservation of the group
No.
or anything.
No.
What are the conditions on H? Or is just H?
H is, I think all we're using that H is a subgroup of G which injects into, as a subgroup, it is also a subgroup of K mod O to the n plus. Nothing else in this argument. But if H is already chosen to be new KO, then it has the maximal rank of anything injected in K mod O to the n, so you cannot have grown up in rank and still be injected into K mod O to the n. H is a billion because it's a subgroup. As a group, it's the same as a subgroup here. Yes. So if you clean up what's going on, so if G is definably semisimple, if you start G, which is K3, then H will have to be normal, because we took H of maximal rank, so we will get now a normal infinite abelian subgroup definable, so this is impossible. So if G is definably semisimple, this is impossible, and we are able to eliminate then, let's see, yeah, no. Okay. Oh, you have 4 buttons, but seems complicated. Yeah, I'll just finish.
So what would you have done with 6?
Yeah. So luckily we are not. Wow. Now I admire all the people who are able to pull it off.
Actually, 6 might be easier because you know what it corresponds to, right? Column, which are the rows, which are the columns, right?
Stop distracting them.
Okay. All right, so now let me just finish. So now we are left with, G, after removing everything, is K3, well, I'll write K, gamma, K mod O3. So if it's finite, we are done, and it means there is no K part, capital K part at all. But if it's infinite, the only way it can happen that if locally inject into capital K, and then you have again new K inside K, but not as a subgroup, just as a Lie group, local Lie group. And now you use, well, this is not in the ACVF setting. In the ACVF setting, things are slightly different. But now you look at the adjoint. This is what we do in periodic case with respect to capital K now of G into GLNK. And the kernel must be finite because so when we show that the kernel is finite. So this is where we got the H1. So now we have H1, more or less, and you can mod out from the beginning all the finite subgroups that came up, and at the end, just be left with these 2 groups, H1 and H2. Because if not, you get an infinite normal abelian subgroup.
And does that work for everything?
Sorry?
Yeah. No, it's just I'm thinking of something. Let's stop.
Okay, that's it. Thank you.
All right, so it's a very nice talk. Other questions?
Can you say something about the first step? Like where do you get this S?
Yeah, it's very elementary. You just look at fibers of, you look at x to the n mod E, and then you basically start looking at fibers. You look at k to the n mod E, and first you find a fiber. So you reduce to one-dimensional sets, so sets of the form basically k mod E, just by looking at fibers. You find one fiber, you have infinitely many classes, or else you can reduce by induction to smaller k to the n. So at the end, you reduce to the problem of just k mod E, first step. And now inside k mod E, you use the various properties that we know of seminimality in the ACVF case, or some properties of periodic field. So you know, the fact that you know how definable subsets in K look like in all these cases allow you to find either a copy of gamma, or not gamma, of a little piece of gamma of K mod O. So you first reduce to that, and then you use in each of the settings what you know about definable sets and definable equivalence relation, just in one variable.
did want to use elimination of imaginary, the immediate logic that we should teach.
Yeah, but that's what I was wondering, how to do it without.
Oh, but you have binary,
Also some utility.
binary, And in the decomic space, K-mode always also have an ordered vector space, right?
No. It's a strange. It's a weakly or minimal without the exchange property. This is actually a nice example of a weakly or minimal structure without the exchange property, and it is not an ordered vector space. It's more complicated than that. Somehow locally it is, but you can have infinitely. You have infinitely. If you take all the scalar product, all the scalars in K, let's say of value which live in O. And then each one of them induces endomorphism of K mod O. This multiplication by a scalar which is small induces an endomorphism on K mod O, but it has an infinite kernel. So you have a lot of locally constant maps, actually, definable. So it's not an ordered vector space. It's kind of a tricky object. That's why also it's not stably embedded, because you can get more and more scalars, and it's not.
It's not stable in characteristic P, it's not stable in the.
No, in characteristic 0, it's not stably embedded. I think not, yes.
I remember there was something.
Please, just a second, I cannot hear intro. Yes?
Sorry, so we don't know whether the Z0 is definably semisimple.
We don't know yet, but I believe that this will be true. But at this point where we are now, we don't know that. But I believe that it will be true once we understand better the work of Dugold, Imi, and Jacob.
I mean,
So what information do you get if you assume that it's a billion instead of semi-simple?
Almost nothing.
Really?
Yeah, I think. I feel like it only works in a place where locally you can squeeze somehow the whole group. But I have a feeling that for a billion, for the other extreme, I'm not sure if the bottom-up approach can.
Even the beginning, even the second step, I guess.
Well, you do know that. So you do know that locally you have kind of a Cartesian product of groups coming from, at least two of them we understand because you get actual groups. The ones coming from gamma, well, not groups, but local groups. The ones coming from gamma are actually isomorphic to gamma to the n locally. The other two are just abelian groups, which are like type definable abelian group in the O-minimal setting in this case. So I don't know, maybe in ACVF we can say more, I'm not sure. But it's really not a method for abelian groups so much.
It's clear that you're going to have some interaction in the mixed case, right?
Yes, well.
Actions of GLNO and some residue thing or something like that.
Yes. But the four of them do not interact with each other, I should say. The four of them centralize each other in elementary extension. The four type definable groups.
Under this assumption, yeah. Under the semi-simplicity.
No. In any group, interpretable group, sorry.
You might need to mod out or something, and then you centralize each other.
No.
After finite.
But they normalize internally.
Why? I suppose you have GLN of O, and it has a quotient which is GLN of K, right? And this, the graph of this.
I'm not saying that there is no interaction, maybe I should, but they do centralize each other on the type definable level. This is what I'm saying.
Couldn't you have a semi-direct product of GLN of O with...
But on the type definable level, it will be a direct product, I think.
What do you mean? Oh, very locally?
Yes. So it will be, you're right, you can have a semi-direct product of O and of K mod O, but on the, when you look at the infinitesimal groups, they will be, it will be a direct product.
All right, so we're getting low on time. We'll have to call off the questions and continue later. Let's thank Kobe again.